Hello students, today we will study about transformers. In today's lecture we will cover the sections 2.1, 2.2 and 2.3 of the textbook, which deals with the why transformers are important to modern life, types and construction of the transformers, and the ideal transformer. First of all, these are the transformers as shown in this slide. You can see that the transformers are applied at different levels in the transmission system. Why transformers are important to modern life? In this case, first of all, we will go into some history that the first power distribution system was invented by Edison in 1882, which was a low voltage level system having 120 volt DC system. To avoid this problem, there was a number of power stations located in different parts of the city, but this problem was removed after the invention of transformers and the development of AC power sources, which we will study in detail in the coming slides. Now we will talk about the construction of transformer. A transformer is basically composed of two windings on a ferromagnetic core. One winding is called primary winding, which is energized by connecting it to the input source. Another winding is called secondary winding, which is connected to the load. If we see in the figure, we note that left side of the core contains the primary winding on the input side. Similarly, on the output side there is the secondary winding. The circuit symbol can be shown as the symbol depicted below. Now we come to another figure where we can see that the primary winding is connected to an AC voltage Vp, while the secondary winding is connected to a load R. Now we see the types of the transformer with respect to its core designs. There are two types. First one is core type, in which each winding is done on a separate leg of the core, and the other type is shell type, in which both the windings are done on the same leg of the core. A physical transformer contains the primary and secondary windings wrapping on one another with low voltage winding innermost. Such an arrangement serves two purposes. One purpose for this would be that it simplifies the problem of insulating the high voltage winding from the core, and the second purpose is it results in much less leakage flux than in the case where the two windings are separated by a distance. Now we come to the types of transformers with respect to its applications. If we see the applications of the transformers, we can classify them into five types. First type is unit transformer. The transformers which are used to step up the voltage at the generation level. The second type is substation transformer. The transformers which are used to step down voltage from transmission to distribution level, and these are mostly situated in small towns and cities. And the third type is distribution transformer. Distribution transformers are used to take distribution voltage and step it down to final voltage at which the power is used. Potential transformer, voltage transformer, which are also known as PTVT, are those transformers which are used to change the high voltage to low voltage but can handle very small currents. Similarly, the last type is called current transformer or CT, which are used to change the primary current to much smaller secondary currents, but the current is directly proportional to the primary current. This fourth and fifth type of the transformers are mostly used in instrumentations and are also used in experiments in some labs or in electronic gadgets. Now we will talk about the ideal transformer. The ideal, in this figure you can see there are two windings. The winding on the left side, which contains n number of primary turns. Similarly, on the right side, n number of secondary turns, ns. The voltage on the primary side is VPT with IPT current. Similarly, on the right side, on the secondary side, the voltage would be Vs and the Is. The main purpose we consider the transformers as ideal is that we are supposing there would not be any losses, because in real life there would be so much losses which are obtained from the resistance, and the core losses, eddy current and hysteresis, leakage flux. So there would be many losses, but in the case of ideal transformers we are considering that there would not be any losses, so that we can easily calculate some problems and numericals just to make a good idea of our transformer. Although it would not be the real value, but it would be almost similar to the real value. There is a factor as shown in the last equation, which is called transformation ratio and is represented by A. A can be calculated by the ratio of voltages, primary and secondary voltage, by the ratio of primary and secondary number of turns, and by the ratio of primary and secondary currents. If we are interested in finding out the quantities on a particular instant, like t is equal to 5 seconds, then if we put t is equal to 5 seconds in the equation, we can find the value of A, the transformation ratio. So similarly, if we have RMS values, we can also find the transformation ratio from RMS values of voltage and currents on both sides of the transformer, as shown in the second equation. What is the voltage polarity? Maybe you have seen earlier that there is a dot in the symbol. As you can see in the sketch of an ideal transformer, there are two dots on the top of the two windings. Similarly, if you see the lower figures, we can see that these dots are used to indicate the polarities of the voltage. In the left figure, in the figure A, the primary and secondary voltages are in phase when the windings are in the same direction, but if the windings are on the opposite directions as shown in figure B, then the secondary voltage and primary voltage would be 180-degree out of phase. As you can see that the sinusoids shown by the blue color are 180-degree out of phase from each other. Now we have some examples, like if we have an AC voltage on input, 50 volts AC voltage, and the turns ratio is 1 to 1, then on the output the voltmeter will also show 50 volt. But if the turns ratio is changed from 1 to 2, the voltmeter will show 100 volts against the input of 50 volts. But if the turn ratio is from 2 to 1, then the 50 volts of input voltage will result in 25 volts on the output voltmeter. Now we see whether the two voltages are in phase or not. In this case, we can clearly see that the sinusoid on the input side is similar to the sinusoid on the output side with two dot polarities at the top of the both windings, which show that the windings are in same direction, so the voltages are in phase to each other. In this case, another case, we can see that the windings are opposite to each other, which result in the primary and secondary voltages having 180-degree difference, and they are out of phase by 180 degree. So now we will talk about the power in ideal transformers. How can we calculate the power? In this case, as we know that power is equal to voltage into current. On the primary side of the core, the power supplied to the transformer is given by P in is equal to voltage on primary side Vp into current on primary side Ip into cos theta p, where theta p is the angle between this voltage and current. Similarly, the power for an ideal transformer can be calculated for the secondary side like P out is equal to Vs cos theta s, where s represents the secondary side. Now, since the voltage and current angles are unaffected for an ideal transformer, so theta p and theta s would be equal, or we can say that the difference between them would be zero. Now we can prove that input and output power are equal. To prove this, we compare the input power until we drive it until it is equal to output power. Let's suppose we start from the output power. P out is equal to Vs Is cos theta s. or we use over here as cos theta, cos because theta s is equal to theta p, so we use theta for both of them. Vs is cos theta, but we know from previous slides that that the transformation ratio A can be calculated by Vs and Vp and Is and Ip. So from those equations, if you can recall, we can find the value of Vs is equal to Vp over A and Is is equal to Ip into A. If we put the value of Vs and Is in the second equation, if we put this Vs value over here and this Is value over here in Is, then we will find this equation where this A can be cancelled by this A in the numerator, and the resulting equation would be Vp to Ip cos theta, which is also equal to input power. So hence proved that input power is equal to output power in this ideal transformer. The same relationship applies to reactive power and the apparent power, which are represented by Q and S respectively. So it can be derived on the similar lines. Now we will study about the impedance transformation through a transformer. The impedance of a device is defined as the ratio of phasor voltage across it to the phasor current through it. So as we know that impedance is equal to voltage over current, Z is equal to V over I. In this case, Z of L is equal to V of L over I of L. But since there is no any circuit components in between the load and the source, so we can also say in this case that it is also equal to Vs over Is, which is the secondary, which is the source voltage and current, source current. I will explain this in this figure, how it is calculated to find the Z bar L, another impedance which is observed from the input of the transformer. So if we know that the ZL is the impedance at the load and ZL, now we want to find ZL bar, which is observing the impedance from the input points. If we observe the ZL from the input point, which is ZL bar from the input point, it would be voltage over current, particularly primary voltage over primary current. If we substitute the value of primary voltage as A into Vs and substitute the value of Ip is equal to Is over A, then we can find that the ZL bar would be basically equal to A square into Vs over Is. But we already know that ZL is Vs over Is, so ZL bar would be equal to A square into ZL. And here A is basically the transformation ratio. To analyze the circuit, replace the portion of circuit on one side of the transformer by an equivalent circuit with the same terminal characteristics. So these two statements would be verified from the next slide when we will replace the portion of circuit with its equivalent circuit. And the second statement goes, the process of replacing one side of transformer by its equivalent at the other side's voltage level is known as referring the first side of transformer to the second side of the transformer. So this is the figure where you can see that Z of L or Z of load on the rightmost side is equal to 4 plus J3 ohm. But we want to, if you can see in this figure, there are two transformers. One is on the left side known as T1, having ratio 1 to 10. Then we have T2 having ratio 10 to 1. Now first of all, we find an equivalent circuit for T2, which would be represented something like this as shown in the second figure. If we see a Z load from the 2 points which are shown on the dotted line, this would be Z load bar or Z bar load, which is slightly different from the Z load because we have reduced the second transformer into its equivalent circuit. Now, as we have studied in the previous slide, that Z bar load is equal to A square into Z load. But we know in the case of T2 transformer 2, the value of A is 10. So A square would be 100. So in this case, Z bar L would be 100 into 4 plus J3 ohm, which would become 400 plus J300 ohm. Now we move towards transformer 1, T1. In the case of T1, the value of A is not 10, it is 1 over 10, and which can also be written as zero point 0.1. If it is zero point 0.1, then the square of zero point 0.1 would be 0.01, or you can say it would be, if it is 1 over 10, its square would be 1 over 100. So instead of multiplying by 100, we will be going to divide the value of z line by 100. As you can see, the z line bar would be 100 times smaller than the value of z line. So if the value of z line is 0.18 ohm plus j 0.24 ohm, then z bar line would be 0.0018 ohm plus j 0.0024 ohm. So now we have successfully transformed the impedance through a transformer. Thank you.